Hello, this is Dr. Armand bringing you your first lecture in General Chemistry 1. In this lecture, we'll be discussing briefly an overview of significant figures and then focusing more on metric to metric conversions. So there are a few topics that kind of overlap from what you learned in uh, basic chemistry or high school chemistry or even the ALEX review course. So those topics we're not going to discuss further, but you're still expected to refresh on those topics. And so what topics are we talking about? These are things like chemical, physical properties and changes. When you learned it the first time, it hasn't changed from when you're learning, the concepts haven't changed for General Chemistry 1. So that's one thing you need to brush up on, especially if you're taking the lab course. There's a few labs that involve chemical and physical properties. Make sure you refresh on states of matter, the rules for significant figures, and rounding. We'll briefly review over those in this lecture. Make sure you know the conversions between the different temperature scales. We have degrees Celsius, degrees Fahrenheit, and of course Kelvin, which is not degrees because Kelvin is an absolute temperature. Make sure you know your metric to standard conversion factors, especially know the metric prefixes. We're going to discuss that here briefly. So metric to standard conversion factors, for example, for length, you should know one metric to standard conversion factor, such as inch to centimeter. For volume, you should know one metric to standard conversion factor, such as milliliters to quarts. And for mass, you should know at least one metric to English conversion factor, like pounds to grams. Additionally, you should know things like how many inches in a foot, 12 inches in a foot. You should know 3 feet in a yard, how many quarts in a gallon, how many cups in a pint, how many pints in a quart, how many ounces in a pound, because these are things we use on a daily basis. Also, and we'll briefly review over this, but you should know simple metric to standard conversions. Today we'll be focusing more on metric to metric conversions. But these are things you should brush up on, and if you look at the basic chemistry reviews I posted online, they will be helpful as well. So on that note, we'll go ahead and get started. So when we talk about units and conversions, we talk about metric to metric conversions, and it's important to know the prefixes and which power of 10 do they represent. And so some of the common ones that we use are things like kilo. So we use kilometers to represent distance. 1 kilometer is 1,000 meters. We use deciliters to indicate volume. So 1 deciliter is 0.1 liters. Of course, in the labs, we may measure things in centimeters or centigrams, likewise millimeters or milligrams. We use micro. When we're doing certain solutions, we may say this is a micromolar solution, which is 10 to the negative 6 molar for 1 micromolar. And then nano, angstrom, and pico, we usually use for things like wavelength, bond lengths, very small distances. So you should be familiar with these prefixes that I have underlined or marked. So before we begin actually doing metric to metric prefixes, I wanted just to kind of recap on the rules for significant figures by doing some examples. So in this series of questions, we want to know how many significant figures are in each of the following numbers. So we look at number 1, we have 3,050. Well, of course, the 3 and the 5 are significant because they're non-zero numbers. Now, this 0 between the 3 and the 5 is a captive 0. So since it's a captive 0, it's significant. However, this 0 is not significant because there's no decimal point. So this would have 3 significant figures. We move to the second number. Here we have a number less than 1. And so the zeros before the first non-zero number are insignificant. So we can go ahead and mark those off. Now, non-zero numbers are significant, and this 0 is significant as well because there's a decimal point here. And so this is 4 significant figures. Next, we have a number in scientific notation. All digits in scientific notation are significant. So this has 5 significant figures. Next, we have 470. So the 4 and the 7 are significant because they're non-zero numbers. Now the 0 here is insignificant because there's no decimal point. And so this would have 2 significant figures. Finally, 10,000 with a decimal point at the end. All of these digits are significant. So this would have 5 significant figures. So make sure you refresh on the rules for significant figures. In this lecture notes I posted for chapter 1, I do include the rules in case you want to refresh over them. Next, we want to round to the following number of significant figures. So in the first one, we want to round to 4 significant figures. So let's go count 4. 1, 2, 3, 4. After the 5 is an 8. Since 8 is greater than 5, we're going to round up. So it becomes 3,576. Next, we have 135. We want to round to 2 significant figures. So after the 3 is a 5, and since it's exactly 5 and 3 is odd, we're going to round up to 4. And so this would become 140 or 1.4 times 10 to the second. Next, we have another number that's less than 1. So again, these zeros are not significant. And then we want to round to 3 significant figures. So the 5, the 6, and the 8. After the 8 is a 2, so we're just going to drop the 2 and the 3. And we get the number. So again, you can write it as 0.00568, or you can write it in scientific notation, 5.68 times 10 to the negative 3. Next, we have 5,756. We want to round it to 3 significant figures. After the 5 is a 6. 6 is greater than 5, so we're going to round up to 5,760, or you can write it as 5.76 times 10 to the third. Next, we're going to look at some operations. And so here with multiplication and division, we want to look at the number in the operation with the fewer or fewest significant figures. So this one has 4 significant figures. This one has 2 significant figures. So our answer should have 2 significant figures. Next, number 2, we have 86.527 has 5 significant figures, and 1.2 has 2 significant figures. However, here we're doing addition and subtraction. So with addition and subtraction, you want to have as many significant decimal places in your answer as the one with the least number of significant decimal places in the operation. So since 1.2 only has a significant decimal place to the 10th, then our answer should be to the 10th place, 85.3. Finally, we have a combination of subtraction and division. So when you have a combination of operations, you want to look at the number, one of the original numbers in the problem, and see which one has the fewer or fewest significant figures. So since 7.08 has 3 significant figures, that means our answer should have 3 significant figures, so 2.11. So just to recap, when you're looking at multiple operations, so a combination of addition, subtraction, multiplication, and division, the least certain measurement or number sets the certainty on the final answer. So since in 7.08 had 3 significant figures, our answer has 3 significant figures. And then lastly, when you have multi-step calculations, it's recommended not to round until the final answer, because if you round in the middle, it'll start to develop error, could develop error in your answer. Now, with significant figures, those deal with measured numbers. So measured numbers are measured by a measuring device. So measured numbers are obtained using a measuring device. So for example, you want to measure length, you use a tape measure. You want to measure speed, you use a speedometer, etc. Now, exact numbers, just to kind of refresh, exact numbers are numbers obtained by counting or conversion factors within the same system of measurement. So if you can count the quantity, it's an exact number. Or if it's a conversion factor within the same system of measurement, it's an exact quantity. So one of the only ones that's English to metric that's exact is 1 inch equals 2.54 centimeters. And this is, again, exact. So what does exact mean? Exact means it has infinite number of significant figures. You know exactly that it is that quantity. So here we have 3.50 feet. Since we're measuring feet, feet is a measured quantity, so this would be a measured number. It would have 3 significant figures. 400 pounds, since pounds is a measured quantity, then this 400 pounds is a measured number. Now 800 atoms, we can actually count 800 atoms, so 800 atoms is an exact number because you can count the number of atoms it has. So again, 800 atoms, you can count the individual atoms, so it's an exact number. Next, we have 7.5 times 10 to the 5th seconds. Seconds is a measured quantity, so this would be a measured number with 2 significant figures. Now we have 1 liter is 1,000 milliliters, so a liter is a metric unit, and a milliliter is a metric unit. So this is a metric to metric conversion factor. So that is an exact quantity. Next, we have 1 yard equals 0.9144 meters. A yard is an English unit or standard unit. Meter is a metric unit. So we're going to English to metric. This would be a measured number, so this is not exact. Next, we have 1 pound is 454 grams. 1 pound is an English or standard unit. Grams is a metric unit. So we're going English to metric. So it's not an exact conversion factor. So again, numbers you can count or conversion factors within the same system of measurement are exact numbers, also including 1 inch is 2.54 centimeters. So here we want to, in these series of numbers, determine the number of significant figures in the following numbers. So again, the first number is a number less than 1, so these zeros are not significant because they're leading zeros. The 0 between the 4 and the 5 is a captive 0. It is significant. So this is 3 significant figures because its unit is millimeters. Next, we have the unit of meters per second. So these two zeros are significant because they're captive zeros. These two zeros are not because they're placeholding zeros. So this one has 4 significant figures. Next, we have 8.5 times 10 to the 8th. This is written in scientific notation, so all the digits are significant. In D, we have 4,500 grains, and you may say, hey, this should be 2 significant figures. But a grain is something you can count, so you know exactly that there's 4,500 grains, so this would be a exact number, so it has infinite number of significant figures. Lastly, we have 1,050, and you notice there's a decimal point here. So that decimal point makes this 0 significant, and this 0 is a captive 0, so it's significant. So this has 4 significant figures. So if this is kind of rusty to you, I'd recommend reviewing over your rules for significant figures. Let's just see who's remembered from the previous slides. So we will know what prefix is 1 gram equal to 10 to the 6th power. So we know that milligram, 1 milligram or 1 gram is 1 e to the 3rd milligram. So there's 1,000 milligrams in a gram. 1 kilogram is 1,000 grams. Nano means 9, so 1 gram is 1 e to the 9th nanograms. Now micro, 1 gram is 1 e to the 6th micrograms. So 10 to the 6th, this would be the micro prefix. So it would be this one. Now we'll continue. Femtogram is 1 gram equals 1 e to the 15th femtograms. 1 gram is 1 e to the 12th picograms. Now you can write it differently as well. You can say, for example, 1 milligram is 1 e to the negative 3 grams. One gram is 1 e to the negative 3 kilograms. 1 nanogram is 1 e to the negative 9 grams. Both of them are acceptable. So what I'm saying is, you may see it written both ways. They're both acceptable ways to write the conversion factors. So here we want to convert decimeter to picometer. So deci is a big prefix compared to pico, so we're going from a relatively larger metric prefix to a smaller metric prefix, so our exponent power should go up. So what we know is that 1 meter is 10 decimeters and 1 meter is 10 to the 12th picometers. So we get this from that chart. So we set it up. We start with decimeters. So in our conversion factor, we put decimeter on the bottom, meter on top. So now we have meter. In our next conversion factor, we put meter on the bottom, picometer on top, and notice all the units except picometer cancel out. Now when you multiply, you add exponents, so 10 to the negative 5th times 10 to the 12th. That would be 10 to the 7th. When you divide, you subtract. So 10 to the 7th divided by 10 to the 1st would be 10 to the 6th. And so this would be 8.7 times 10 to the 6 picometers. Now again, this makes sense because we're going from a relatively large metric prefix compared to picometer. So therefore our exponent power is going to increase. Here we have another one. We want to go from 6.78 times 10 to the 8th picoseconds to milliseconds. So again, we already have the conversion factors of second to picoseconds and seconds to milliseconds. So what am I going to do? I'm going to convert picoseconds to seconds to milliseconds. So let me draw my train tracks. So we have 6.78 e to the 8th picoseconds. Now since we're starting with picoseconds, it goes on the bottom. So 1 e to the 12th picoseconds is 1 second. Now that we have seconds in our next conversion factor, seconds goes on the bottom and milliseconds go on top. So 1 e to the 3rd milliseconds in 1 second. Now when we multiply, we add. So here we're going from pico, which is a relatively small prefix, to milli, which is larger than pico. So therefore our exponent power should decrease. So our power of our exponent should be less than 8 if we did it correctly. So when we multiply, we add. So 10 to the 8th times 10 to the 3rd is 10 to the 11th. When we divide, we subtract the exponent. So 10 to the 11th divided by 10 to the 12th gives us 6.78 e to the negative 1 milliseconds. You'll notice that our exponent power decreased, which is what it was supposed to have done. Now we're going to go to squared metric units. So we want to convert picometers squared to micrometers squared. Now here we may not know the squared conversion factors, but we do know the normal conversion factors. That we know that 1 meter is 10 to the 12 picometers and 1 meter is 10 to the 6 micrometers. So the way we get the squared conversion factors is we square both sides and we get the squared conversion factors. Now when you square a power, you just multiply that power by 2. So 12 times 2 gives us 24. 6 times 2 gives us 12. It's very important that you remember to square the exponent or raise the exponent to the squared power. Most common mistake is students forget to do that. They just square the unit. It's very important that you square the power of the exponent. So now we have our conversion factors. So we start with picometers squared. Since we're starting with picometers squared in the conversion factor, picometer squared goes on the bottom, meter squared goes on top. And then the second conversion factor, meter squared goes on the bottom, micrometer squared goes on top. Now 10 to the 5th times 10 to the 12th is 10 to the 17th divided by 10 to the 24th. That means you subtract, you get 10 to the negative 7. Now this makes sense because we're going from a relatively small prefix to a larger prefix. So our exponent should decrease, exponent power should decrease. So we'll look at another one. Here we want to convert kilometers squared to nanometers squared. And we're given the normal conversion factors. And again, this should be a meter, not second. So the first thing we need to do, we need to square the conversion factor. So 1 meter squared is 1 e to the 18th nanometers squared. Again, 9 times 2 gives us the power of 18. 1 kilometer squared is 1 e to the 6 meters squared. So what we're going to do, we're going to take kilometers squared, convert it to meters squared, convert it to nanometer squared. So let me draw my train tracks. So we start with 8.23 e to the negative 4 kilometers squared. Since we're starting with kilometers squared, it goes on the bottom in the conversion factor. So 1 kilometer squared (1 e to the 6 meters squared). Now we have meters squared. We're going to go to nanometer squared, so meter squared goes on the bottom. And nanometer squared goes on top. So what we do is when we multiply, we add exponents. 10 to the negative 4 times 10 to the 6 is 10 to the second. 10 to the second times 10 to the 18th gives us 10 to the 20th. So that equals 8.23 e to the 20th nanometers squared. Now, does that make sense? Yes, because we're going from a large metric prefix to a smaller one, so our exponent should increase. And since it's squared, it's going to increase quite a bit. So this answer does make sense. So one more example with squared, because it's a very common one students trip up on. So here we want to convert decimeter squared to nanometer squared. So again, we give them the conversion factors of meter to decimeter and meter to nanometer. To get the square, we're going to have to square those conversion factors. So 1 meter squared equals, now 10 is the same thing as writing 10 to the 1. So 10 to the 1 squared would be 10 to the second decimeters squared. And then 1 meter squared, 1 e to the 18 nanometers squared. So what are we going to do? We're going to convert decimeters squared to meters squared to nanometers squared. I draw my train tracks. So start with decimeters squared. And again, we're going from a relatively large metric prefix to smaller metric prefix, so our exponent power should increase. Since we're starting with decimeter squared, it goes on the bottom. Meter squared goes on top. So again, what's on top? We multiply exponents. When we multiply, we add exponents. When we divide, we subtract exponents. So 10 to the 8th times 10 to the 18th is 10 to the 26th divided by 10 to the 2nd gives us 10 to the 24th. So this would be 2.37 e to the 24th nanometers squared. So again, this answer makes sense because we're going from a relatively large, we're going from one prefix to a prefix smaller than that, so the power of the exponent should increase. Lastly, we're going to do a cubic conversion. So here we want to convert millimeters cubed to nanometers cubed. And so what we know is that 1 meter is 1 e to the 3 millimeters, and 1 meter, 1 e to the 9 nanometers. So now what we're going to do is we're going to cube these conversion factors. So we're going to multiply the powers by 3. So we get 1 meter cubed is 10 to the 9th millimeters cubed, and 1 meter cubed is 10 to the 27th nanometers cubed. So we start with millimeters cubed, and again, we're going from a relatively larger prefix to a smaller prefix. Power of the exponent should increase. So since we're starting with millimeters cubed, it goes on the bottom in our conversion factor, and then meter cubed on top. And then from that, we're going to go to nanometer cubed, so meter cubed goes on the bottom, nanometer cubed goes on top. Now again, look to see that all the units cancel out. So 10 to the 4th times 10 to the 27th, you add the exponents, you get 10 to the 31st, divided by 10 to the 9th, that means you subtract. And so you get a final answer of 10 to the 22nd. So there's 7.5 times 10 to the 22nd nanometers cubed. And as we predicted, it makes sense because we're going from a large metric prefix to a smaller one. So lastly, I wanted to do a dimensional analysis problem to kind of prep us for what's to come in chapter 1. And so in dimensional analysis, you may have multiple steps in order to solve a problem. You may even have to draw an illustration. And you may have to use conversion factors that you know, or even in the problem, it'll give you conversion factors. So in this problem, it talks about during World War II, the British used radar to detect incoming enemy aircraft. The radar will send out a radio wave. It gives you the speed of the radio wave, 2.998 times 10 to the 8 meters per second. That would reflect off the aircraft and back to the radar. Based on the amount of time it took the radar to receive the reflected waves, the location of the approaching aircraft could be calculated. So it says if it takes the radar 1.60 milliseconds from when the radio waves is sent to receive the reflected wave, what is the distance of the aircraft in miles? And it gives us a conversion factor for miles to kilometers. So I'm going to draw a little bit of the coastline of England. Let's say we have a radar station here, and we have a plane here. So what it's saying is it sends out a radio wave. It hits the aircraft and it comes back. And so this whole time it takes 1.60 milliseconds. So if we just want to know the distance of the aircraft, we want to know how long it took the radio wave to reach the aircraft, and that would be half of the time that was recorded. So this would be 0.8 it would be 3 significant figures. Again, this is milliseconds. So now how are we going to solve this problem? Well, we have the time in milliseconds. We're going to convert it to time in seconds. And then once we have the time in seconds, we can find the meters because we know it's velocity. And then we can find kilometers and then ultimately miles. So what do we know? We know, for example, that 1 second is 1 e to the 3rd milliseconds. We know that 1 second is 2.998 e to the 8th meters. We know that 1 kilometer is 1,000 meters, and we know that 1 kilometer is 0.625. So these are the conversion factors. Some we knew, some we had to get from the problem. So now let me set up my train tracks. I think this is all we need to know. And you can do this in several steps. I'm just going to do it all in one step, but you're welcome to do several steps. So we start with our 0.800 milliseconds. So we're going to convert milliseconds to seconds. So we know that 1 e to the 3rd milliseconds, 1 second. Next, we want to convert to meters. So we know that in 1 second, it travels 2.998 e to the 8th meters. Then we know we got to convert meters to kilometers. So 1,000 meters, 1 kilometer. And then we know that 1 kilometer is 0.625 miles. So everything on top you multiply, everything on the bottom you divide. And the computer spits out 149.9 miles. Again, you shouldn't round them to the end. And so now, since this involved many different types of units, we got to see which conversion factor or number had the fewest significant figures. So 1.6 milliseconds is 3 significant figures. 1 second is 1,000 milliseconds. That's exact because it's metric to metric. 1 second is 2.998 times 10 to the 8th meters. That has 4 significant figures. 1 kilometer is 1,000 meters is exact because it's metric to metric. And 1 kilometer is 0.625 miles. That has 3 significant figures. Put mile at the bottom. So we need to round this to 3 significant figures, so it becomes either 150 point or 1.50 e to the 2nd miles. Either one is acceptable. So again, when you have a combination of different types of conversion factors and numbers, you got to look at see which number has the fewest significant figures. And in this case, it was 3, so our answer should have 3 significant figures. So that concludes the lecture on metric to metric conversions and a review of significant figures. What I would recommend is watching this video again when we get to the practice problems. Pause the video, see if you can work out the problem, and then check your answer by playing the video again. On that note, the next lecture will be over metric to English conversions, doing dimensional analysis, so solving word problems. Other than that, until next time, Dr. Armand signing off. I hope you enjoyed the lecture and you learned something from it.